Hello, everyone. Welcome to the Toronto Geometry Colloquium. This is a weekly series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we're going to have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
And today, we're thrilled to have Dr. Mackenzie Leake as a, sorry, hold on a second. My apologies, we're having some technical difficulties there. So as I was saying, today we're thrilled to have Dr. Mackenzie Leake as our opener to talk about paper-pieceable quilts, and Professor Caitlin Mueller as our headliner to talk about sustainable architecture. As a reminder, if you have any questions for the two very exciting speakers that we have today, you can type them either in the YouTube live chat, which we'll be monitoring and asking your questions at the end, or on our Discord channel. So let's go straight to it. Our first speaker today is Mackenzie Leake. I had written in my script, but I just learned that she is Dr. Mackenzie Leake. So she was a PhD student at Stanford University and will soon be starting a postdoc at MIT. Just two small town institutions. You don't need to remember the names. It's probably not important. Anyway, I'm really honored to be able to host her today and to talk about quilting. She's one of those unique researchers who has taken on a project all the way through from the user interface that's like front facing to the user to the very deep theoretical math graph theory side of a single problem. So and I'm hoping she'll go into depth into that today. So thank you very much for coming, and you can take it away, Mackenzie.
Great. Well, thank you for that introduction. And let me share my screen. Okay, great. So thank you for having me. And today I'm really excited to talk about our recent work from SIGGRAPH called A Mathematical Foundation for Foundation Paper-Pieceable Quilts. And this is joint work with Gilbert Bernstein, Abe Davis, and Manish Agarwala. So the art and craft of making quilts presents many exciting geometric and design problems. And in this work, we focused on one particular quilting technique called foundation paper piecing, which is used for making pieced quilt tops. So in this process, quilters sew pieces of fabric to paper guides. And we learned that many people sew patterns this way, but few people actually design them. And to start, we wanted to learn what makes designing these patterns challenging. So each pattern has both the visual design and the sewing order. And it's the sewing order that's really complicated to develop. So if you draw an arbitrary pattern, it's likely not paper pieceable. So currently, pattern designers use trial and error to identify sewing orders, usually by hand. Unfortunately, this is very tedious, and designers might just give up if no ordering can be found in the first few tries. And these design constraints come from the required precise sewing process. So to do this, we start by cutting fabrics to fit over the corresponding regions of the design. We layer the fabrics in a specific way to attach them to the paper, starting with flipping the paper over. And then we place the first fabric over region A1 face up. And then the second fabric on top face down along the seam line between A1 and A2. So we layer the fabrics, leaving a 1/4 inch seam allowance next to the sewing line. And this layering process will ensure that the fabrics align with the proper regions while hiding the seam allowances. And so next, we flip the stack over again and sew along our seam line. And then we flip our stack over again. And then fold our fabrics into place. So now both fabrics are right side up. And then we repeat this process of layering, sewing, and folding with the blue piece for region A3. So then we can just tear away the paper, and this leaves us with a complete design. So while the process I described led to a precise design, it has some constraints. So these constraints include proper layering, flatness, and no refolding. And so if I layer the fabrics in the way that I described previously, the stitching and seam allowances are hidden and the fabrics are properly oriented in the end. So for example, here, the red piece is sewn on top of the green piece properly, and this will lead to a smooth finished seam. I keep the paper and fabrics flat and do not refold any of the fabrics once they are sewn. But if I violate these constraints, I do not properly hide the stitching and seam allowances. So here on the right, I am violating the layering constraint. So I attach the red piece incorrectly under the green piece instead of on top. And so this results in the edges of the green fabric being exposed instead of hidden. So we know that there are constraints on this particular construction process, but are there designs that would always make us violate these constraints? So for example, is this design paper pieceable? And it turns out that this Y-junction pattern actually has no feasible sewing order. So I tried one order here, but it won't work. And it turns out that no matter in which order I sew the seams, I will eventually have to violate the flatness and refolding constraints. And there are many other designs too that would cause you to have to violate our constraints. And it's not immediately clear just from looking at the geometry which designs will work. So for example, if we look at the two designs on the right here, they look very similar at first glance, except for the seams highlighted in pink. But the top one is not paper pieceable and the bottom one is. And it's not just the geometry of the design that matters. So paper piecing imposes constraints on the sewing order as well, and not every order will work. And so when designing a pattern, two questions we need to ask are, is a given design paper pieceable? And if so, in what order should I attach the pieces? So to answer these questions, we mathematically formalize the paper piecing process as reachability in a state transition system. We construct a certain type of hypergraph that represents the geometric design and construction process. And we show that a design is paper pieceable if and only if this dual hypergraph is acyclic. So let's take a look at a few definitions that help us prove this main result. So first, we define a paper piecing design as a planar mesh with faces corresponding to fabrics. And then we need a way to describe the sequence of one or more interior edges that border a single face to accurately reflect the sewing process, which involves attaching one face at a time. So we define a seam as a set of all of the interior contiguous collinear edges that border a single face that is not a subseam of any other seam. So here are the seams for this design. And now that we have defined seams, we return to our simpler paper pieceable design. And we want to think about how to construct a dual graph based on this design. And we need a graph structure that captures the sewing process of adding faces one seam at a time. So in this dual hypergraph, every face is a node and every seam is a hyperedge. And to build our hypergraph, we start by adding nodes for the faces. And then we add an orange hyperedge for the orange seam and the blue hyperedge for the blue seam. And here we are adapting the concept of hypergraph acyclicity as studied in databases to the specific properties of our application. So now let's look at a more complicated example of constructing a hypergraph. And we start by adding all the faces as nodes and then identifying the seams. So the purple seam forms the purple hyperedge, the green seam forms the green hyperedge, then pink, orange, blue, and finally red. So notice here that each hyperedge corresponds to a single face on one side. For example, the red hyperedge with face D. And now we need one more key element, leaf hyperedges, which help us to determine if a graph is acyclic and compute a sewing order if one exists. So here's a design with 5 faces and its corresponding hypergraph. So leaves are hyperedges containing a node that is not a member of any other hyperedge. So in this case, the orange and green hyperedges are leaves because E and D are nodes that belong to just a single hyperedge. So recall our 2 key questions. Is a given design paper pieceable? And if so, in what order should I attach the pieces? So now we can use a greedy leaf plucking process on our hypergraph to answer these questions. So let's take a look at this leaf plucking procedure for a simple block. So there are 2 available leaves here, the blue one with node A and the red one with node C. And here we can pluck either of these leaves. And so at random, we'll choose to start by plucking C. And now there's just one leaf, the blue hyperedge with node A, so we pluck that, and then B, and then finally D. And the reverse of this leaf plucking order gives us a valid sewing order, which we can then just apply to the pattern. So now let's try another design. So here's its starting hypergraph. And the only available leaf here is the blue one with face D, so we pluck that. And we can now look for another leaf, but this time we're stuck with no more leaves to pluck. And if there are no leaves to pluck before the end of our procedure, the hypergraph contains a cycle, which means the design is not paper pieceable. So we provide an interactive design tool based on our algorithm to allow users to create their own designs. And to use the tool, a quilter drags and draws seams, and the tool will indicate if the design is paper pieceable. So here we're drawing the pot for a cactus plant. And now we'll add a seam that makes the design not paper pieceable. So the tool alerts the user to this by highlighting the seams involved in the hypergraph cycle in red. So we adjust the size of the pot to make the design paper pieceable, and the red lines disappear and the sewing order becomes visible again. And we continue adding detail to the design, keeping the design paper pieceable with each additional piece that we add. And we end up producing this finished paper piecing design and sew it. We also make several other designs like this banana and this camera and this house. And using our tool, we also created these 9 leaf designs, which we combined into this quilt top. So to learn how a quilter would incorporate our tool into a typical quilt design process, we asked an experienced quilter to work with the tool over a few weeks. For one of her designs, she started with a sketch, which she was unsure at first how to turn into a paper piecing design. She then used our tool to generate a valid sewing order automatically, and then sewed this design. She then sewed 3 more blocks and assembled them into a full quilt. So this process shows how developing an algorithm to check for paper pieceability helps us design better tools for quilters that fit within their existing workflow. And offloading the difficult step of computing a sewing order allows the user to focus on the visual design. And this is just one example of how geometry can be a powerful tool for capturing some of the complex steps and decisions that happen in creative processes. And embedding this knowledge in design tools enables us to support long-standing craft traditions, as well as create new opportunities for design. So with that, thank you for your attention, and I look forward to talking with you in the Q&A at the end of the session. Thank you.
Thank you, Mackenzie. That was a great talk. I'm really looking forward to the Q&A and to see, I'm assuming, close-ups of all the quilts that you have behind you. So thank you very much for that talk. As usual, we'll now move on to our headliners talk, and we'll have a joint Q&A for both at the end. So make sure to write your questions. Caitlin Mueller is a professor at MIT working on structural design and architecture. And last week, we heard a really great talk from Liane Makatura, also a PhD student at MIT, who talked about optimizing simple shape designs for some parameters, as you may remember. And that's why I think it's great that we have Professor Mueller to speak today, who in a way, among many other things that she does precisely that shape optimization, but on steroids, not for like simple shapes, but buildings and macro structures. And she has a really important access to data optimizations, which is sustainability, critical for today's world. So I really hope she'll tell us about that too. Thank you very much for coming, Professor Mueller, and you can take it away now.
Excellent. Thank you so much for having me. Are you able to see my slides?
We are.
Wonderful. So I'm assuming I'm one of the more unusual speakers in this series because I'm not coming from computer science or geometry processing, but hopefully you can see the connections to how some of the ideas that are being developed in the geometry world can really make an impact at the scale of buildings and infrastructure. And so my talk is titled New Forms or Geometries of Sustainable Architecture, Computing for Performance and Delight. As Sylvia said, I am an associate professor at MIT, and I have a research group here called Digital Structures. And all of the work that I'll show today is collaborative with this team of graduate students and postdocs One of the things that's special about our group is that we're really interdisciplinary. So some of us have architecture backgrounds, structural engineering, mechanical engineering, applied math, computer science, and we're united in bringing these disciplines together to solve issues at the building scale related to design and construction, motivated both by the beauty of this type of approach to design and also by important issues related to sustainability. I first want to highlight the beauty part here. Structures and buildings and infrastructure that are designed where engineering and architecture are really integrated together are some of the most amazing buildings in the world. These are structures that discover a new form through mechanics, through engineering, through constraints, rather than fighting against them. And it's really an expansive and broad way of working in a design context. I say this because sometimes people think that using engineering or mechanics in a design context is limiting or overly restrictive, but hopefully you're convinced of the opposite. All of these designs are very different from each other. There's a diverse palette here, but what unites them is that they all use material in very thoughtful and efficient ways, and they are able to resist loads through geometry, through their shapes. So high performance design, all of these are high performance design. So diverse pursuit, it's architecturally rich and intellectually elegant. At the same time, climate change is an enormous crisis that we're all facing as humans, but also within the discipline of architecture, this is an incredibly important challenge. Buildings contribute 40% of global climate emissions, and those emissions are both due to the operation of buildings and to the energy and carbon emissions embodied in the materials due to extraction, transformation, production, transportation of construction materials to the building site. And embodied carbon emissions vary enormously across different design concepts or building typologies. These are two Olympic stadia from recent years, both beautiful designs. There's a 14x differential in their embodied carbon use per seat. So the Beijing Olympic Stadium on the left uses 14 times as much embodied carbon as the London Olympic Stadium on the right. We would not see a 14x performance differential in any other engineering discipline. We wouldn't have two cars on the highway with a 14x differential in fuel efficiency. That's illegal. But in buildings, this has persisted for a long time because we haven't paid attention to these metrics. But the context today demands that this and other performance metrics play an active role in design. In some ways, we're in this position because of amazing technological development in recent history. So in the last century or two, we developed new materials that enabled new spans and new forms that we've never seen before. And we've also developed new computational tools that allow us to design, represent, and analyze new structural ideas, new architectural ideas that move beyond the realm of hand calculations. And these ideas have made their way into practice and are now normative in today's construction industry. So we're in this era where we really can do anything we want today, and we often do. But our current context demands that we move beyond that. The questions of the last century of possibility, what is possible to build and how might we build it, need to be replaced with the urgent questions of what we should build and how we should build it. And my belief is that we need to do this by using performance as a guide in design. But that's actually very challenging to do. If we look at a design process, as we move from the early conceptual phases all the way through construction, we gain more and more knowledge about the object that we are designing, which gives us the opportunity to do more and more thorough analyses and simulations. But we also lose freedom. So if we are all the way at the end of the design process before we consult engineers, we can't improve the design. We can only tell whether it works or not. So early conceptual design, where we have a lot of chance to make good decisions, is where we need information from engineering principles and simulation, and yet it's challenging because of this fuzzy resolution. We also have a challenge of discipline. There are two disciplines that work on buildings, architects and structural engineers, that are separated from each other in many ways. We're separated culturally, academically, disciplinarily, professionally, and yet literally these two disciplines are talking about the same thing they work on, literally the same physical thing. And yet the way that computation is engaged, the way we think about fabrication and materials, even educational styles and pedagogy are very isolated in many parts of the world between these two disciplines. So my belief is that we need to bring these two fields closer together to empower more integrated design and construction processes where design thinking and engineering thinking can be interlinked in synthetic ways. I'm not the first person to worry about this. This has been a common complaint among architects and engineers for 60 or 70 years. So these are articles written in the 50s and 60s on the same topic. If you read them, it feels like they were written today, which is really frustrating. And so I think we need a new way. We can't just complain about our differences, but we need to find new ways to collaborate and work interdisciplinarily, both between individuals and between sources of knowledge. And one way I think that's very compelling that we can use today is computation. First, computers were used to design buildings. And one of the key examples is the Sydney Opera House shown here. And the structural engineering firm Arup, who worked on it, used finite element analysis for the first time to engineer this building, not hand calculations. And while that was both very empowering, it was also actually frightening to the people involved. And they held a symposium on how computers should be used in engineering and design for buildings. And they comforted themselves by saying that the computer can't take the act of designing away from an architect. It doesn't possess an imagination. This worry remains very present in today's discourse within architecture and within engineering. We're really concerned about autonomy and authorship, and yet we know that the computer can do more than what we ask it to do today. So let me give you an example of how computers are used in today's typical workflows in the design of a building. If we have architect and engineering teams, a lot of times we'll start in the architect's office, and the architect will start by doing what we call ideation, coming up with different design concepts that they like for various qualitative reasons that meet the goals of what they've set out. They'll pick a design that they think is especially compelling, and then they'll send it over to the engineer. And this is a very long process. Finally, the engineer can run a simulation, and these numbers are not good. The engineer says, this design doesn't work. We can't use this design. So we go back to the architect's office and we try another one, and we send it back, and we really hope this time it will work. And we get the answer, and okay, good. We can use this design, it works. Let's build it. I think you can all imagine why this is such an ineffective process. We've only really considered 2 out of the infinite spectrum of possible designs that we could conceive of. And the engineer has only been engaged in a really trivial manner of basically a checker at the end of the process. And yet about 85% of buildings are designed this way today. How can we make this better? One way is to improve the connection between ideation and simulation, or design and analysis. So if we can more quickly link these 2 processes, we can shorten the time and we can iterate more and consider more alternatives. But this is still basically guess and check or trial and error. We can make this more systematic by parameterizing the design problem and setting up what we call a design space with design variables or sliders, and link this into a more integrated workflow. I'd say this is about 3% of buildings use processes like this at the conceptual design phase, and this is still just trial and error. If you're an engineer, you think the answer to this problem is obvious. Once we have this acyclic graph, why don't we connect it all together into an optimization problem? And indeed, in many disciplines, this is what people do. We would have an objective function that we can measure from our simulation and use that to drive an organized search through the design space to an optimal solution. This is almost never used to design buildings today. And why is that? Is that because it's too technical or too challenging for the architecture and engineering disciplines engaged in buildings? They just don't quite get it mathematically? No, it's not that. It's that this process is a really poor approximation for the actual human design processes that have designed the best buildings in our culture and history. And a lot of my work is in response to this problem. I'm interested in the power of systematic design and optimization, but also in addressing the challenges that it confronts us with, because it's not exactly applicable in its current state to the design of something that's as human as a building. So specifically, what's wrong with this? Why doesn't this work? First of all, optimization is designed to give us a single solution. It's a fully automated process in most cases, and it's really hard to have control as a human in what's happening. And that's by design. In many cases, that's intentional. But for the design of a building, that's not what we want. We want to be able to interact with the process and have some say in what's happening. The process can be very slow compared to the way a human designer typically works. We don't want to wait hours or days or weeks. We want something that's instantaneous. It can be very unnatural to parameterize a design problem. It's very different than the way a human typically works in an open-ended design workflow. Sometimes you do this whole process and then the answer you get is very obvious, so it undermines the entire purpose of what you're doing. We need these tools to surprise us and give us new ideas rather than reinforcing things that we already know or sending us in boring directions. And then finally, a lot of this work is not materialized, meaning a lot of the ways we design on the computer are divorced from realities of construction and material behaviors that are actually critical in design drivers. So all of these are issues that I'm interested in confronting in my work that I'll show you now, but hopefully you kind of get a sense of the context in which I'm working, which has a lot of opportunity for impact, but is also challenging because of the intrinsically human nature of architectural design. And before, just as an interlude, I wanted to share this much more compact version of what I just said. This is from an exhibition from the designers and architects Charles and Ray Eames, who in an exhibition asked, ought form to derive from the analysis of function? Should form follow function? I think many people think, yes, of course. And their answer is, the great risk here is that the analysis may be incomplete. And in the design of architecture, analysis is always incomplete. There is always a holistic, qualitative, conceptual side that is critical to the success of the building that we cannot formulate in the computer. But we can formulate some parts. And so I think this idea of a design space is still really powerful. And a lot of my work uses parametric design spaces as a way to understand relationships between design and geometry and performance and behavior. So this is a really simple design space. This is called a truss. This supports loads, could be in the roof of a building or a bridge. And what's really interesting about trusses is that their geometry affects performance substantially. If I change the location of the lower left node up or down or left or right, the amount of material that the truss needs to support the load changes, sometimes quite substantially. And that means that the truss basically performs better or worse. It needs more or less material, has more or less embodied carbon, its environmental impact varies. Using algorithms, again, that were developed before I was born, I could find the optimal solution in this space quite quickly. I could find a local optimum, I could find a global optimum. But again, this is very rarely used. And maybe part of the reason why is those designs don't happen to be very interesting. But the space itself actually contains a really rich variety of designs that we almost never look at in traditional optimization. But in fact, if we do look at them, we might start to get new ideas. Here I'm showing designs that fall on the contours that are 10, 20, and 30% worse than the absolute optimal design. And you can see that there's increasing diversity in their geometry, and their performance is still acceptable. So as a human designer, this is a really interesting subset for me to start to consider and add additional holistic analysis of my additional qualitative constraints that I haven't been able to tell the computer about. I don't only want the least weight truss, I want a low weight truss that is also beautiful, contextually appropriate, and creates the spatial conditions I'm interested in. I develop a lot of computational tools and methods to try to exploit that tension. This is one of the first tools that I made when I was a PhD student called StructureFit that works on shaping trusses. It uses something called an interactive evolutionary algorithm to co-evolve designs with human designers. It searches through the space and finds high-performing subsets of designs that it presents to the user. These are also filtered by diversity. So it's trying to show us designs that are visually distinct and high-performing. And then we as designers can see how they perform. The number represents performance. A lower number is better. It's normalized. So less than 1 means it uses less material than the original design. And then we can interact with this by choosing the designs we find most interesting. And then this back end algorithmically recombines them and presents new options for us. And in some ways, this is like optimization, but it's a way to capture an objective function that we could never write down. It includes the mathematical part of structural efficiency, but it also includes the qualitative or even subjective part of my own preferences. And in this work, we also see the opportunity to have direct manipulation, which I think is really important in any kind of design tool. We want to have final control, especially at the end as a designer, on the shape and understand how that affects performance. A process like this, even though it's really simple on just these 2D trusses, can generate a lot of interesting solutions. Here, these are arrays of designs. On the left is the geometrically regular boring design. Those all use the most material. And as we move from left to right, the amount of material required goes down. All the way on the right, we see designs that we found in history to also be very high performing. These were designed using analytical methods akin to optimization, but we can also find designs that we would never find with optimization that again represent some kind of balance between different goals that we have, some expressible and some not. So this idea of a design space catalog can be applied in many typologies and many structures. This is a long span roof with a space truss. Again, the geometry is critical to performance. It's not an accident that the designs that use less material have more interesting geometries. And if we start to consider this in 3D, we see an even broader range of interesting solutions because three-dimensional force flow has even more diverse ways to be efficient. And so these kinds of catalogs can reveal this to us. This can be applied very flexibly. This is in floor plans of buildings, looking at where structural walls should go. And there are things that we can measure about performance of walls that resist wind and earthquake loading, like they should be centered, the center of rigidity should align with the center of mass. But there are still many, many ways that we can do that. And so having this catalog helps us as designers understand kind of alternatives and spark new ideas. This idea can also be expanded to multiple performance objectives, and there's lots of work in multi-objective optimization generally. I think for buildings, it's incredibly relevant because there's always a trade-off between embodied energy and carbon and operational energy and carbon, meaning the energy required to condition a building might increase if we make the building more structurally efficient. And we see that here in this shell-like building, where as it becomes taller, it has more air to condition and a larger surface area to transfer heat across, but it's also more structurally efficient. And so multi-objective analysis also creates catalogs of Pareto optimal designs that can allow us to understand kind of trends related to, for example, here we're doing this in different climates. We see different types of Pareto optimal designs, but it also allows us to combine disciplines in ways that we typically don't. So instead of just optimizing for the best structure or for the best energy performance, we can start to see this as a way to compromise between disciplinary and professional boundaries. I'm also interested more broadly in generating really diverse catalogs of designs. These are sketches made by leading structural engineers from the past several decades who in early stage design typically use sketching as a way to do ideation. And very few people around the world can do this. This is really only accessible to these experts. But what's so amazing about this isn't that they're really good at doing calculations, it's that they come up with a really diverse set of ideas so that we can basically brainstorm as broadly as possible and identify really compelling candidates within these sets. It's incredibly hard to do this computationally because it's hard to parameterize a problem that can so broadly represent diverse concepts, typologies, and topologies. And so another area of my work looks at that question of how to formulate really diverse and broad design spaces. And this parametric design framework in which geometric features are varied in order to create variation can only get us so far. It's still rather limiting in terms of the self-similarity of the set. If we move into a rule-based or so-called grammatical design space, sometimes this is a subset of procedural modeling and computer graphics, we see a lot more variation and a lot more variety. And the reason is that this is not, there's not a fixed length vector representation of these designs, but instead they're generated by applying rules in a particular sequence, but in a very open-ended way where rules can be applied infinitely. And so in some of my work, I've used rule-based design to generate structural systems that are both really visually diverse, but also high-performing. And this is an example of a bridge that we could generate with a grammar. And in my work, I like to embed structural principles into the rules themselves. So I'm not just operating on shapes, but I'm also operating in the world of physics and can therefore generate really diverse solutions that are all in equilibrium under loading and that all vary from each other very significantly. And if I randomly sample this algorithm that generates these bridges 50 times, I can get a really, really wide range of design options, again, that are all following structural principles and find, again, more familiar and also less familiar design options through this kind of brainstorming process. We've combined this kind of generative procedural modeling technique with a way of modeling statics called graphic statics, where we're able to operate in both geometry of form and geometry of force simultaneously. And I won't say a lot about this today, but I think this is a very compelling field that may be of interest to the geometry and graphics world in greater detail. Here, the value of it here is it gives us, again, really wide flexibility in generating new and interesting forms that are all guaranteed to be in equilibrium in pure tension and compression. So they're all really materially efficient at the same time. Here's another example where we're trying to take this into 3D and trying to start to understand performance. And we're excited about this as a way to generate incredibly diverse and new ideas that still perform well. A problem with everything I've shown you, however, is that these design spaces can become impractically enormous. So for example, for that long span truss roof that I showed here, if we were to parameterize this in a rather simple manner, let's say the coordinates of control points, I had 36 variables and I sampled them at a resolution of 4. This is how many designs I have. Here's me looking at a very, very, very tiny percentage of the design space. It becomes impractical for me to actually understand this in any kind of breadth or comprehensive manner. Even if I can use simulation to study how they perform or behave, how efficient they are, it's still overwhelming. It's really hard for me to make sense of this. And so while these computational design spaces, I think, are very powerful, as they become more valuable, as they become larger and more diverse, they're also harder and slower for us to navigate. And so recently, I've been really interested in this question of how to tame this chaos from a data perspective. And so if we start to think of these design spaces as large data sets, we can start to apply technologies from data science and machine learning to make sense of them and to develop new representations of them that are more human legible. One of the ways I do that is with a technique called surrogate modeling, which is actually a really old idea that, again, in other engineering disciplines is pretty common, hasn't really been used in buildings until recently. But the idea is to replace slow simulations with instantaneous approximations using regression models. And the argument for this, again, is that in a creative design task, we want instantaneous feedback from a computer. I would say 200 milliseconds is a good limit for how much we're willing to wait for the computer to respond if we're trying to stay in the creative flow. Surrogate modeling is really compelling because once you have some training data, you can build an approximate model that then can be sampled instantaneously to give you reasonable estimates of performance and performance metrics in real time. And so, for example, what this means is that we can sculpt the design for a shell and get a full response instantaneously through the surrogate model. Here it's predicting X, Y, and Z displacement of the shell under loading. And we're not bothered by sending this to another program or running code. It's just happening live within this really interactive sculpting environment, within a CAD environment. And this starts to move things that used to be verifications into really design inputs. We can start to use this information to guide our design. We can also use this not only to predict displacement fields, but even to predict for another shell, the entire optimal distribution of material within that surface. So this is the result of a topology optimization algorithm, which you may have seen. Traditionally, this is rather cumbersome to set up and takes a lot of time to get a result, but we can use surrogate modeling to approximate the result of a real topology optimization that gives us a very, very fast answer and allows it to become a design input. So here's some examples of the training data that we generated. And on the left are the data, on the right is the prediction. The error is not 0, but is reasonably low, and the speed is significant. We save 2 orders of magnitude in speed using the surrogate model. And what that means from a design perspective, again, is that we can be in this real-time environment, sculpting and modeling and exploring geometry and understanding structural and material implications instantaneously. Here, we're projecting that topology optimization information into an actual 3D model, so we can start to see what this would really look like if we were to build it and understand its implications. We can similarly use this information in a more abstracted way where we take the topology optimization result and use it to size elements in a waffle slab-like structure in order to, again, get this sort of real-time information where we've significantly compressed the traditional process of conceptual abstract design and final materialization. Now it's all in this one instantaneous feedback system. Surrogate modeling has the limitation that it's only as good as its training set, and it does require a lot of time to generate good training data. Almost all the training data we use in our own work is synthesized from our own parametric models. So lately we've been working on how to make more generic surrogate models that can be used across problem types or across design processes. And so we've recently shown that by combining graph-based surrogate models or graph convolutional neural networks with a little bit of transfer learning, we can do things like train a model on designs for a bridge, and then with a small amount of additional data, get it to actually be accurate at predicting the behavior of a tower. And so we think this is a really compelling way to start to make surrogate modeling even more portable, transferable, recyclable, and so it can really start to make an impact in practice. So we think this is a really exciting way to make design faster and more interactive. Once we have this feedback, what can we do with it? How do we use it in a generative way besides just looking at the information? We're also interested in using computation not only to give us feedback, but also guidance to help us generate and find new solutions that we wouldn't find by ourselves. On the most basic level, one of the things we can do is start to cluster the design space, to try to organize the design space into things like families. So we start to give hierarchy and order to something that is otherwise chaotic and disordered. So this is one technique we use a lot in our work. But often we want more than just a mapping or an organization. We want actual guidance. We want to know where should we go. We don't necessarily want optimization, but we want kind of a clearer understanding of our problem. And one way to express this is that design variables or parameters are often really indirect ways to access what we care about. We really care about these performance metrics, but we can't operate directly on the performance metrics in a direct way unless we solve some kind of inverse problem. We really usually we're at the input are always these design variables. So we've been very interested in trying to address that and thinking about how do we find better links? How do we reparameterize our problem so that the design variables represent variation or meaning in terms of performance? So for example, here, using a very old statistical technique, we've shown that we can synthesize or find linear combinations of original variables that correlate best with performance metrics that we care about. And if we do that with principal component analysis, we can get each of these rows is a synthetic or linearly combined variable that recasts our original kind of dumb variables into these smart directions in the design space that are meaningful to move as designers and as people who care about performance. We can make this even more sophisticated by considering this in a nonlinear way. So recent developments in machine learning and specifically in things like variational autoencoders can help us create dimensionally reduced latent spaces, which are really powerful because, again, they can kind of recombine our original variables into something new. We can project ourselves into this new meaningful landscape that can be very low dimensional, as I'll show you, but also critically, we can project ourselves back out. So this can be a generative tool for discovering new designs. In our work, we do this in a way where we condition the latent space according to performance. So we want to find a latent space that contains high-performing designs. And the output is something like this, where we've compressed the 36-dimensional latent space into something that's only 2 dimensions. A human can literally look at this landscape and move through it. Interpolation is meaningful, so we can smoothly move from one design to another. And we have a smooth change in both the appearance of the design and in how it performs. So we can go from this slightly chaotic version to something really organized and understandable and really focus on the fun part, which is discovering new designs and new forms. This latent space exploration can be combined with surrogate modeling so that all of this can be compacted into a new kind of user interface for design that leaves kind of the world of sliders behind and brings us back into the world of design objects and maps across them. So we think this kind of latent space exploration is really exciting. we're interested in how this can really be used in real design problems. And of course, there's still a lot of work to make this more accessible for non-experts. And we're also really interested to think about what this means in a multi-objective landscape. Finally, in this area, stepping back even further, how do we make these processes even more human-friendly? The latent space still requires some kind of parameterization at the beginning. Someone needs to set up the original variables. That process is by nature unnatural and cumbersome for many people. And so in this recent project funded by the National Science Foundation in the US, we're interested in having one step further back, where our interface is not, doesn't start out with design variables, but starts out with the most human form of design thinking, which is sketching on a pen and paper. So as I showed you earlier, some of like the best designers from history, or this is my student who's also a wonderful designer, we often start in this very primal form of expression. And we can combine this with a lot of recent advances in machine learning. And I'm sorry, I won't show you exactly how, but our ambition here is to try to take sketches and project ourselves into these performance coded latent spaces so that we can start to do things like sketch different design concepts for a problem. And here we're sketching within fixed typologies. So we have these curved frames, these trusses, and these boxes. From the sketch, we want to get an estimate of performance, and we can do that with fairly traditional surrogate modeling with convolutional neural networks. So with enough training data, we can predict the relative performance of these designs. And then with the latent space, we can then find designs that are in between our sketches. So we can use interpolation in the latent space to start to discover compromises or collaborations or new ideas, and even try to bias that interpolation according to performance. So can I find better performing versions of the original design that I sketched? And that this can be a really interactive process in which the human and the computer are operating really within the language of the human, which I think is our ultimate goal. We also think about how these ideas can be taught in an educational perspective. So for the last few years at MIT, my colleague Renaud Deneuve and I have been teaching a class called Creative Machine Learning for Design. And we're in the process of developing this as a MOOC that will be on the MITx online platform. And I hope it will launch at the end of 2021 in a few months. So if you're interested, please keep an eye out for that. We also distribute a lot of tools that encapsulate the methods that I've described. A lot of our work is in this platform called Rhino and Grasshopper, which are really popular in the architecture and design communities. And one of the really nice things is that there's a large open source movement of people sharing tools and code within this Grasshopper framework. So we also have our tools available in that framework if you're interested. And then finally, in the last part of my talk, I want to talk a little bit about getting these designs out of the computer and into physical reality. Because a lot of times when I show people these designs and I say, these are really efficient, they're efficient in some theoretical sense on the computer, but once we actually need to build them, they could either be incredibly complex or incredibly expensive. So I'm also interested in addressing that challenge. I think just because something is expensive in our current context doesn't mean we shouldn't do it. Our climate demands that we start using less material and in the way that we design. But luckily, we have ways to address this, not by simplifying our designs or standardizing them. I think that's the wrong direction. I think we need to move towards real material efficiency in the future. But we can do this by changing the economics of construction. And one of the ways I'm most interested in that is by exploring recent advances in digital fabrication and robotic assembly, not to automate our current normative practices, but to really expand what we can do and help us really materialize these new forms generated on the computer. So as an example here, I'm morphing this truss lattice to become more and more efficient. But as I do so, the length of every element becomes different. Every node becomes different. A traditional contractor would tell you that would become cost prohibitive. But with digital fabrication here, this robot is extruding a lattice. You can't see the robot, but it's a 6-axis robotic arm with a 3D printer extruder. It's making a functional lattice here. It doesn't care if every node is the same or different. So it's just as easy for it to make something like this, where the shape is driven by structural performance, where there's this beautiful resolution between the aesthetics and the form and the performance. And it is, from a construction perspective, it's neutral. It's just as easy to make this. If we scale this idea up, there are companies and people who are working on large-scale construction robotics. This is a company in Tennessee who have a large-scale system where they can extrude building-scale lattices. And so we worked with them on this structurally optimized bench. The lattice on the bottom is the extruded part, and in the reflection, they filled it with a lightweight foam. This starts to be a way to understand fabrication and complexity in a new light, where the geometries that are driven by efficiency become equally possible. If we move even further to new geometries and topologies that are efficient, we can look at, again, something driven by topology optimization in this case. The resulting design on the right is a very efficient way to transfer load from the top to the bottom of the structure. And it's also incredibly irregular. It would be very hard to figure out how to build this by hand. And even with a robot, it's very hard because the assembly sequence and the toolpath planning is non-trivial. In our work, we've been connecting with state-of-the-art advances in robotics, specifically in task and motion planning, where we have a lot of algorithms that exist for solving other types of problems, but have rarely been applied to architecture and construction. But we can start to use those to make these types of designs really realizable. So for example, this is a topology optimized beam that we can design on the computer and build with a robot relatively easily. And this robot is building a beam that I would personally never be able to build by hand. The robot has, in its planning algorithm, it takes into account the mechanics, not only of the final structure, but at every step, it's making sure that the structure will be stable. So it's incorporating physics into the assembly sequence. The sequence also makes sure that the robot won't collide with itself or the structure that's already built as it's going. So with these advances in algorithmic task and motion planning, if we can figure out how to apply them in a design context, it can really unlock new geometries and forms for us. And what we're hoping now is that we can do this fast enough that right now this is a little bit slow, but we're getting faster and faster. We really want this to become something that we can design in response to rather than something that we do at the end. And then finally, more practically, thinking about materials and construction, we can apply these same ideas to extremely pragmatic and ubiquitous systems. One of the places in a building that has the most material and wastes the most carbon and energy is the floor system. You may think that the floor is not doing too much, but the floor is the first place that loads in a building are received. And it's almost always an incredibly inefficient system. For example, a solid concrete slab is usually wasting 50 to 70% of the material. It's not needed structurally to support loads. It's there because it's easier to build a flat rectangular slab than it is to carve a material structurally. But in our work, we've seen that because this is so impactful from an environmental perspective, it's really worth considering. And it can be a spectrum. We're developing platforms where if you don't want to go all the way to the most complicated sculpted shape, you can still start to use these ideas of material efficiency to dematerialize your system. And we think that that should be something where the fabrication opportunities inform the design process. So for example, this is one of the tools we've built for optimizing these concrete floor systems. It works with normal concrete materials that are in use today and with normal building codes. So everything here is extremely normative and accepted today. The only thing that's new is the geometry. So we're really using new geometrical representations and combining them with classic analytical techniques to find new forms that are efficient but also buildable. And so, for example, we built a prototype with partners outside of Delhi who have a particular type of formwork system that they like to use, which is bent steel plates, singly curved bent plate. They laser cut the individual pieces and spot weld them together. We were able to change the parameterization of our problem so that only buildable structures in that system were contained, and then optimize within that to find a structure that uses the least material given that system. And we were able to fabricate full-scale prototypes and test them and prove that they really work, and they're ready to be deployed. We also find this really interesting from an architectural perspective because these new shapes and structural forms also change the character of the space and give new opportunities for spatial expression. In interior design, it's incredibly common for people to add fake beams to their ceilings to add character. We can add real beams that are structurally optimized and incredibly beautiful by really celebrating structure and making it a critical part of the architecture. And we think that's both a sustainable and conceptually a strong design idea. The last material here that I'll show is timber, which is another material that's gaining a lot of traction. It's used in many parts of the world that have forest resources and increasingly is seen as a sustainable alternative to conventional materials. It's also an amazing material because it can be machined incredibly easily. And yet what we're seeing in what's called the mass timber movement, which is the movement to make large scale timber elements that can create tall buildings, they're almost always these standardized bulky parts that again are wasting most of the material that they're using. So by using the same ideas of structural shaping, we can start to really use material only where we want it, combine this with new additive manufacturing techniques, and create a new visual and aesthetic palette for interior spaces. We can also consider timber more speculatively, and this is the last project I'll show. In this work, we're looking at using timber not in its processed traditional state, but in its natural state, where we see in architecture a desire for non-standard forms, and yet ironically, we almost always make them by machining standardized material stock. What if instead we took available material in its natural, organic, irregular state and used that as the driving point for the design? Here in particular, we're working with tree forks, which are amazing structural connections. They're cantilever moment connections in trees with incredible internal fiber structures that transfer load incredibly efficiently. We could never 3D print the internal fiber structure of a tree with today's technology, and yet this is abundantly available in trees that are cut down every day. So we are working with local partners. For example, this is the city of Somerville, where they're cutting down trees as necessary for a construction project. Normally, trees that are cut down are chipped and turned into landscaping. All of the carbon that is sequestered in their cellulose is released within a few years back into the atmosphere. If instead we can keep those parts and find ways to use them structurally, they can become, for example, structural nodes in a pavilion project. And here we've developed a computer algorithm that can take a digital inventory of this found material and optimally allocate it to the target design. And then we can change the target design in response to the material inventory to try to have this back and forth conversation between the desired form, its structural behavior, and the materials we have available. It's also becoming more possible to do this from a fabrication perspective, again, because of digital fabrication, where things that might have been originally very time-consuming and labor-intensive, like working with all these irregular parts and debarking them, can be automated through robotics, where the path planning and all of the geometric processing is automated so that we can create these nodes in a rapid and flexible manner. And then what we end up with is basically a kit of parts. It's like a Lego set, except all the Lego pieces come from these trees, but they prescribe the exact geometry, so the final assembly of the structure is incredibly simple. All of the angles at which the members need to connect to the nodes are pre-programmed into the tree fork. And so this, in the end, is actually very low tech when we're actually on site. So we've offloaded all of the complexity to the prefabrication part. And really, this is all driven by the geometry of the trees. So we think this is really an exciting way to reconcile design intent, structural efficiency, available resources, and the constraints of fabrication. And we think in general, upcycling is a really important area of future work in terms of environmental impact, but also in terms of computation and algorithms and geometry. And I hope to see a lot of work in this area in the coming years. So to conclude, I hope you're convinced that computing is a wonderful way to explore both creativity and performance in architectural design. We need to consider performance, but we also need to do so in a way that is respectful of design processes so that people will really use these methods. So we think this balance between systematic design space exploration, free and flexible creative processes, and economical digital fabrication processes can combine to really enable a more sustainable future for our built environment. Thank you very much.
Thank you very much for the talk, Kidlin. That that was amazing. I really love these animations of the 3D structures changing over as you explore the design space. We're gonna go to the questions now. We're a little over time, so I'm gonna just go straight to it. The first question is for Mackenzie and her work on paper quilting. So this is a question I have because maybe I missed something, but many of the examples that you showed are basically you have a very, very clear first leaf from where you to start, and later it's kind of like very deterministic that then another leaf appears and you kind of like pluck and pluck until you're done. And it's very satisfying. But I was wondering, what happens when you have many possible leaves to start? And like you showed the example where you start plucking and then there's a point where there's a cycle and you can no longer, will you reach that state regardless of which leaf you start, or can you accidentally create something that's impossible if you start from the wrong spot?
Yeah. So thank you for your question. Yeah. So it turns out that we were able to show that actually you can just choose at random and start from any of the leaves, and you'll end up with the same either invalid or valid kind of pattern in the end. So you can start anywhere. And so for right now with our tool, we just do choose that randomly. But something we're interested in is in talking to quilters. Sometimes there are kind of sewing specific constraints around maybe starting with bigger pieces or kind of criteria like that. And so something we're kind of thinking about in the future is how do you pick among those orders in a way that kind of makes sense for the domain.
Okay, that makes sense. I guess that's a theoretical result, right? That
Right.
It's either invalid or non-valid or
Right.
valid, right?
Right,
Okay.
right. So that greedy approach is kind of a big part of being able to kind of implement it this way. So.
Makes sense. Thank you. It's great to see like how much theoretical richness the problem has. Professor Mueller, we know you might have to go at some point, so I'm going to ask you all your questions now. So in case you need to excuse yourself, and then we'll go to the rest of Mackenzie's questions, if that's okay with everyone. So first question, many of the amazing results that you showed today are in 2D. Is 2D already a very practical realm? And what is the remaining work needed to generalize it to 3D?
Yeah, I mean, on the one hand, I think 2D is a great place to start because it's always good to start with the simplest version of your problem. And many structural systems are essentially two-dimensional. And many buildings have kind of orthogonal layups of systems, and so 2D can be sufficient. However, I will say that the potential for really discovering new means of load transfer becomes richer in 3 dimensions because typically those systems are what we call statically indeterminate, meaning there are many ways that forces could flow through them, and it results in typically a wider variety of possible solutions. So I think it's fairly problem dependent, but in general, architects and engineers do work still a lot in 2D because that sort of relates to how a lot of buildings are actually constructed. So I'd say both.
Okay. Next question. There's a gap between the approximate models that are used during optimization and the eventual constructed bridge/building, etc. Does it ever happen that the design that I've discovered in procedural modeling becomes very far from Pareto optimal when realized in the final construction? Yeah,
I'm wondering what the source of the gap that this person is worried about. Is it a source? Is it because of an inaccuracy in the simulation? Maybe. Let's
yeah, I'm imagining it's like building error. Like that was my interpretation. It's not my.
Yeah, I mean everything about buildings today is very approximate. Construction tolerances on site are on the order of a centimeter, and so we're
wow.
there's always imprecision. I think a lot of building typologies are fairly robust to that, and so if you found something that you think is Pareto optimal and you have a reasonable abstraction of it in your conceptual model, which is very important, then it will be true. However, there are certain typologies that are incredibly sensitive to small changes, and shells are one of them. Two shells could have very similar geometries, but have really, really different performance values. And so that is something to be careful about. And so I'd say certain typologies require more precision than others.
Okay, Makes sense. I'll try not to think of that like centimeter tolerance as I'm in like the 33rd floor of a building right now. My last question is kind of more of a philosophical one. So, we as a society, we give this power to people we call architects who have like studied and gotten a degree that's like regulated by some government. And at least in my country, I don't know how it works in the US. The architect signs the plan of the building, and that signature is kind of like, society has empowered you who studied architecture to make the decision that this building won't fall and sanitation will work and that sort of stuff, right? If a neural network designs the final design of a building, how informed how should we reevaluate that societal consent that we give to people with your degree of architecture?
Yeah, that's a great question, and certainly an important one. So all of the work that I'm interested in here is about conceptual design. And I'm not necessarily, even though I'm showing like, oh, and it can go all the way to the material phase, I am not imagining replacing all of the detailed engineering and architecture and simulation processes that typically happen later in the design process to ensure all of these important things that yes, when you stamp or sign for a building, that you are putting your professional reputation on the line for. I think we definitely still need to do all of that. But I'm trying to replace these somewhat arbitrary processes of where does the original design idea come from? The original design idea, if not following one of these processes, is either an idea you've seen somewhere else or something that you kind of remember from a previous project, or the design process is mysterious, like when it's purely human driven, but also not likely to lead to solutions that are ultimately very efficient. So I'm trying to replace that part, but not the entire rest of the chain of engineering. I think we can't reduce all of that right now to a neural network in any way that is at all safe. So I think it's still a partnership between different disciplines and areas of expertise, but I'm trying to have this compressed, quick model that can run in the beginning to help us make good decisions before it's too late in the design process.
Okay, thank you. That's important nuance. Right. So the human in the end runs the simulation to see that it doesn't break and actually signs. Got it. Perfect. I'm really excited to see it, in the real world. Okay, so if you need to go right now, you can go. Thank you very much for staying late. I know that part of the lateness is on our side, so thank you for that. We'll now move on to the questions we have for Mackenzie. A group of geometry processing experts listens to your talk. Obviously, the questions you're going to get is, how can we generalize it? So we have two questions about generalizations. First, all your seams are like straight lines, and I don't know anything about sine, but I imagine you could do curve patterns. And how would that affect your algorithm? And could you generalize it to curved seams?
Sure. Yeah. So currently, as we kind of consider things, we do only consider straight seams for now, and most of that motivation is from just the particular application domain. So quilters do sew quilts with curved seams, but often not using paper piecing, and that's largely because of the paper and getting fabric to stretch and or clipped properly, and getting all of your kind of seams to lay flat while attaching them to paper is really hard. You really need that degree of flexibility that you get from sewing without the paper involved. So I think that in very, very rare cases do people actually try to do a gentle curve this way. And so I think that there's kind of, that speaks to then this question of, well, are there really cool applications in curved piecing and so forth? And I think there definitely are tons of them. I don't know that they're foundation paper piecing probably isn't the right technique for it, but I think that there's a whole other space of really neat problems there.
Okay, so maybe the answer to the next question is the same, but what about non-planar stuff? Like sometimes you make quilt on something that's like more spherical, that has a curvature, not just the plane. So how would that work with your algorithm?
Sure. Yeah. Again, so I think that's a whole other space of really neat things, particularly if we think about not just kind of supporting what's necessarily currently done in quilting, but thinking about how we can use geometry to support, other forms that people don't currently do. And I think that, for right now, like, yeah, paper piecing again is this very kind of relies on this kind of flatness and kind of 2D structure and so forth. But I think that there are a couple of cool examples of people doing kind of folded fabric work or kind of quilted 3D shapes and so forth. And I think that again, there's tons of opportunities using kind of other sewing techniques for thinking about taking those seams and not aiming for a kind of flat traditional quilt.
I see. Okay. Then my last question, just because I saw you're talking, like when you're introduced to a new problem, you're trying to like think of all the ways you can break it to completely understand like the fundamental. So you have these you have these patterns that are sort of impossible, right? Non-viable. And I was wondering if you by breaking existing pieces into smaller sub pieces, can you turn a non-viable pattern into a viable one?
So generally, it's a little careful. So just arbitrarily no. So the kind of general way that people do make a non-paper pieceable pattern paper pieceable is either just removing a bad seam. You can extend a new one in some cases and carefully, and then often you need to introduce a section boundary. So our project largely revolves around these single section paper pieceable designs. You can sew the entire thing on one sheet of paper, but one way that you can kind of break it, have that notion of kind of breaking it up or adding seams to make this possible, is that you kind of add a seam line which breaks it into multiple sections, and then each of those might be paper pieceable. And so so right now people, our tool will indicate when you might need to do that, but it's up to the user to actually do that. And something that we're really interested in is thinking about, well, how could you could you do that automatically, and and how could you kind of fix these patterns in these other ways?
So you would like then saw those independent pieces together.
Right. So you like each individual section would then be paper pieceable, and then you would use another standard sewing technique without having to worry about the kind of paper being in the way and sew those other seams that you need then.
I think that's great. I think you're creating a lot of quilting fans in our lab right now, just after this talk. Where do you think newcomers can start in this area, both on like the practical side, like how can you start with quilting, and also like what are fundamental problems mathematically that one can start with?
Sure. Yeah. So I think that on the quilting side, I think actually the pandemic has been really wonderful in the sense that there are a lot of online tutorials and groups and quilt guilds and things like that that make it possible for more people to learn how to sew. I think that just sewing together patches of fabric is something that anybody can learn. You can do it by hand. You can use a sewing machine. Even paper piecing, it's very procedural. There's kind of steps that you go through. Kind of something special happens the first pieces you attach, and then you just kind of go from there. And so it's also, I think, once you learn how to do that, it's fairly beginner friendly as well, and it's a very friendly community overall. And then I think on the on the kind of geometric and algorithm side, I think that this is my first geometry related project that I've done, and I think a lot of it, so my direction came much more from being excited about the domain. And I think that there it's really just if you approach things from that angle, then it becomes looking at things you love to make and understanding what's hard about the problem. Are there ways to represent it? Discussing with other people, and getting different views. I talked with many different people, and we talked about many different types of graphs and ways to represent the problem. And I think just spending a lot of time to kind of do that and figure out a way to describe it, that is the key piece, and so forth. And then from there, you can see what you can do algorithmically and theoretically to kind of support what you want to support. And so I think that for me, at least, I really enjoy coming in with kind of the application and then working with other folks to kind of figure out, what's really happening here and how do we explain it and so forth.
Thank you. Thank you. So that's all the questions we had, or at least all the questions I can ask without going massively over time, which it is already. So let's end by thanking both our speakers again, as well as Hannah Locke, the designer for this past week's or this session's poster. And we'll see all of you next Friday at 10 a.m. Eastern time to hear from Duygu Ceylan and Emily Yu. Have a great day, everyone.